Thanks again for inviting me. So today I'll be talking about swatting the hardware security bugs. Um, this is a joint work with our friends at Intel and TU Darmstadt. And this work is based on a paper that we wrote for Using Security 2019. And the work has progressed from that paper. Um, and this is based on competitions that we have been hosting at many top hardware security conferences, including DAC, CHES, and now at Usenix Security as well. And I will talk more about it. Okay, so what's happening here is that, as Daniel nicely mentioned, there has been a lot of side channel attacks that have been coming into picture. And people have been enforcing a lot of security solutions in the hardware. There are dedicated chips, there are trusted execution environment, there are runtime protection techniques. Some of them are also targeting embedded systems, capability systems, and there is obvious wrong. So more, as you see, more and more security techniques are percolating into hardware, and this is not new to this community. And many of these techniques are coming not only from academia, but also from industry. And even these techniques exist for the latest RISC-V architectures as well. But as people like Daniel Gross are exploiting many of these loopholes in the actual architecture, they undermine the security of the entire system. And recently, we have seen a plethora of these type of cross-layer attacks. Basically, they exploit many of the flaws in the microarchitectural design, and they expose it to the end user. And so attacker who have least privileges, they can still exploit these cross-layer bugs and achieve their goals. And one of the important thing is that, unlike software, where it is easy to patch, hardware is very tough to patch in silicon. And that's why it calls us to patch these bugs while the design is under production or under design. Rather than if you trying to patch a silicon that has been already shipped out, it's too difficult. The game is maybe already over. Okay, but what I'm going to talk about is this level of hardware security bugs that are one level or multiple levels below the microarchitecture, right? So if you look at how people typically design hardware, many designers, they use standard hardware description languages like Verilog or VHDL, and this level of description is called a register transfer level. And people, there are lots and lots of designers who do that. And these RTL codes are then translated into registers, wires, transistors, things of that sort, using standard electronic design automation tools. But the question is this RTL secure, right? Do we trust the designers to do a proper job of writing this RTL code? So let me explain from a hardware security development cycle. So this is a security development cycle from Intel, but I believe many companies have a similar security development life cycle. So what people typically do is they do the design exploration, finding what is the hardware that targets a particular market segment. Then they go and figure out the architecture and the microarchitectural design. And once you have once you tailor down the microarchitectural details, then people go and implement it in RTL. So that is where the designers come into picture. And then this RTL, people do not trust the designers completely. So they need to do a verification step where they check whether the RTL code is indeed implementing the desired microarchitectural details or not. And once this RTL code passes the verification step, then they synthesize this RTL into transistors, wires, and things of the sort, and they fabricate the chip. And post-fabrication, they test the chip for security bugs, not only for security bugs, but also for manufacturing bugs and things of that sort. And if it passes, then they deploy the chip and provide support. And one of the common themes that people have encountered in the last decade is hardware Trojans. And Trojans, typically, people consider, hey, these are the chips that are fabricated at a place that I do not necessarily trust. For example, a foundry located in the offshore and things of that sort. So then the attacker in the foundry can insert malicious circuits into the chip, and they are called Trojans. But on the other side, if you look at the design phase, there are many places where mistakes can happen. For example, in the architectural space or in the microarchitectural space, or even the RTL design. And many times these bugs are unintentionally introduced and need not happen from a malicious sense, but even like common design mistakes can lead to security bugs. And there are two broad classes these days. One is the microarchitectural, which is the predominant class, where we talk about Spectre, Meltdown, and those type of attacks. But on the other hand, what I'm going to talk about is the mistakes that people make in the RTL code and how they get exploited by the software. Okay. So many companies, including Intel, figured out, hey, this RTL design is going to be a problem. So what they do is, along with the IC design, they also supplement this IC design with a security development lifecycle. So as and when they define the architecture and stuff, they analyze the threats, they identify what are the type of tests that they need to run. And when they have the RTL design, they analyze the RTL code for bugs and stuff. So to this end, they perform security testing, not only on the RTL design, but also on the fabricated chips, because if you have the chip, you can run many of the tests a lot faster than doing the software simulation. And finally, when you get the design back, you have to, and you ship the design, you have to support for attacks that can be uncovered in the field. So if you look at here, typically the security development lifecycle uses a bunch of tools. Most of them are simulation based, where you simulate the hardware design, particularly the RTL code for a particular environment, apply test vectors, see the responses, and see if they match your desired. And hopefully you can catch the bug by then. And also you can use a bunch of formal verification tools to analyze the design. But as we all know, formal verification are very powerful in telling that there is no bug, but at the same time, they suffer from scalability problems. So what people typically resort to is manual RTL inspection. So they train a bunch of engineers, and hopefully you get lucky, you can catch the bug. If you don't pay them well, or if they are not doing, if they are having a down day, then the bug can slip through. And finally, hopefully in the field, they try to patch things as much as they can, but many bugs that slip through this design phase cannot be patched, and we will see so. Okay, so in my talk, I'm going to focus on how do we verify the RTL code for security properties, and this work is not new. There have been a lot of techniques that people have developed in the last 10, 15 years or so. So the first one is proof carrying code. This approach is similar to the proof carrying code for software programs. The idea is when you buy an RTL code, or when you design an RTL code, you use COG-based proof assistant platforms to verify that the given RTL code satisfies the given security properties or not. But the problem here, the good news is this proof carrying code can ensure that the security properties are indeed met. But the problem with this type of approach is that it's very slow. Like, for example, even when you want to verify the security property of a single AES core, it takes like 30 minutes. And think about a complex hardware design, including processors, or even a system on chip with not only processors and memories, but also like bunch of other modules. This design gets this type of approach gets increasingly complicated. Okay. The next one is model checking. So this is like along the lines of formal verification tools. A lot of people use bounded model checking, so where they take the design and they convert it into an equivalent SAT formula. And then you also develop handwritten security properties that you think the design should satisfy. And then you encode those properties into SAT formulas, and then you do bounded model checking to ensure that whether the given design satisfies it or not. So this has been a well-known mechanism, and people do use it because if it passes, it's great news that the design always ensures the security property. But the biggest problem is that this type of approach, they do not scale well for large scale designs, including a processor with 20,000 gates. Okay. And the other approach is, again, is from the software security community or programming languages community, which is the information flow tracking. The idea here is you have a source and you have a destination, and let's say you are trying to send the secret message from the source to destination. You want to ensure this secret message only goes from source to the destination and not to anyone else. So you do a path analysis to ensure that this information does not get leaked. So the same thing you can extend not only for confidentiality properties, but also for integrity properties. And that's what information flow tracking techniques do. Again, in the last 10, 15 years, there have been a bunch of great work on porting information flow techniques for both gate level and RT level designs. And now there is also good language support for IFT, for Verilog, and other hardware description languages. But the problem with IFT is that it generates a lot of false positives, and it's up to the designer to weed out through the false positives and see if there is actually a bug in there or not. And finally, as you see, a lot of attacks are now coming up at a cross layer, and people need to verify not only the hardware, but also the firmware that is running on top of the hardware. So for that, there is a new approach called instruction level abstraction. But this approach is still not at accurate. It's still at its infancy, but it seems to be promising. So as you see, these are the traditional pre-silicon verifications that people use. But if you analyze each and every technique, you can come up with a bunch of limitations for them. So for example, they do not seem to scale well, especially for cross-modular designs. As you know, in a system on chip, the designs are highly modular. And if you have a security property or a security sensitive design that span across multiple modules, these techniques do not scale well in ensuring those properties. And the next thing is these techniques do not tend to model the cache state gap behavior well. Hardware tends to have a lot of memory. And when I say cache, I not only refer to the actual cache, but also like bunch of registers and other memory modules. These techniques do not seem to model them well. And third one is the timing flow. So with respect to hardware, timing actually matters a lot. So when you try to incorporate the timing properties, it even reduces the scalability of existing techniques. And finally, not but not least, there is a good gap between hardware and software. And when you want to verify the security properties of the entire system, you should not only consider the hardware, but also like what is the software that is running on top of the hardware. And cross-verifying the properties across both hardware and software, these techniques do not seem to scale well. Okay. So to this end, we want to motivate the community to come up with new techniques to detect bugs in hardware. So for that, we started with a competition called HackerDAC back in 2018. So it's still running now. There is DAC 2021 happening, and I will talk about that. And the idea here is we want to understand these hardware security bugs in RTL. We want to motivate the community to come up with new techniques. So for that purpose, we took an open source RISC-V test bed, and we deliberately injected security bugs in them. And we didn't want to inject any bugs, but we want to insert the bugs that is more interesting to industry and academia. So for that, we collaborated with our friends at Intel. So they were very good in creating bugs, at least for the RISC-V SoC. And to this end, we organized the competition. More than 54 teams from industry and academia participated in 2018. But since then, the competition has grown to several hundreds of teams and students participating in this event. So I will present not only what happened in the competition, but also on the effectiveness of using current industry standard tools on detecting these bugs. Okay, so first let me explain the how do we build a buggy SOC? So for that, we use two SOCs. One is called the Pulpino SOC. The other one is the Pulpissimo SOC. So one for the preliminary phase, one for the final phase. And we went to identify the CVEs of many hardware and firmware bugs that are already there. And one of the important conditions that we picked while injecting these bugs is that these bugs should be software exploitable. Because if you think about it, at the end of the day, we can have a buggy design, but the bug is only as good as the exploit. So that is why we were focusing on bugs that are software exploitable. And as I told you before, we work with Intel engineers, and of course, Intel cannot give their own designs. They cannot give their own RTLs for everyone to go and find bugs in them. So that's why we have to recreate many of the bugs from the CVEs through Intel's expertise on this open source SOC. So this is a RISC-V-based SOC. This SOC has many features: memory bus, peripheral registers, cryptographic modules, debug and JTAG interfaces, and boot RAM. And the idea here is to have many of these diverse modules so that it can give a rich environment for participants to identify bugs. And also for the organizers, for us, it also gives us a rich environment so that we can inject different types of bugs into different modules. And the type of bugs that we have been working on, they have been dealing with denial of service or privilege escalation, but it can also leak sensitive information. And just want to remind again that all these bugs are software exploitable. Okay, so we have a comprehensive list of the type of bugs that we inserted. I'm not going into the details. The full list of bugs is there in our paper, but it's also there in our GitHub repository. So interested people can go and look into it. But I want to just focus on some of the bugs just to give you a deeper idea. Okay, so this is the diagram of the SOC that we have. And as you see here, we have the RISC-V core, and it has two buses. One is the memory interconnect, the other one is the APB bus. And it has a bunch of modules that came along with it. So in this SOC, we injected a bunch of bugs across many different modules. So some of the examples include memory access violation. And so this bus is designed poorly in such a way that the memory addresses overlap, and this will allow an untrusted peripheral to access the memory region allocated to a trusted peripheral. So this way, an untrusted peripheral can have higher privileges than it was not supposed to have. And why this bug is interesting, because in order to catch this bug, you have to not only focus on the individual module, but also you need to focus on how two modules talk with each other over the hardware bus. And for that, you need to model the semantics of the bus protocol. Too many modules are involved. And this turns out to be a big problem when it comes to industry standard tools for verifying such type of bugs. The other one is information leakage. So here the SOC tends to use an AES, but the bug is that the key for the AES is stored in an unprotected memory. And in fact, we figured out many of the common designs that are out there tend to store the AES keys in an unprotected location, and that can be read by an attacker. So this is a simple bug. But the thing is, from a detection perspective, using tools, this is interesting because you should not only model the AES from the hardware perspective, but we should also model the firmware that is doing the storage of the keys. And modeling both hardware and firmware together in one environment is very challenging. And there are not many tools out there, there are not many techniques out there that can help you to verify both hardware and firmware together for many security properties. And so that's why we believe that this is like a bug that will be out there in many systems in the field. And bug 7 is memory access violation. And here, this is a classic example of an RTL bug. The finite state machine of this decoder is badly written in such a way that if you send two faulty transactions, you get access to the to the protected memory. So I will explain more about this soon. And the next, so let me explain how one can exploit these type of bugs in software. So what's happening is, if a core is trying to access a legitimate memory region that it was supposed to give access, the AXI memory interconnect, it is indeed giving the access. But if you try to do an illegal access, the AXI memory interconnect should deny the access and create an interrupt. So this everyone understands, things are fine. But what happens is that the RTL for this memory interconnect is badly returned in such a way that if you send two consecutive access, the second access gets passed through. So even though it is illegal, the RTL is badly returned such that the second access gets passed through. And therefore, an attacker can access the memory range. And again, just to put it in the context with respect to the previous talk, these are the type of security bugs that are one level below the microarchitecture. These bugs arise because the RTL design, the Verilog VHDL codes that people write, have lots of bugs in them, and those bugs get exploited from a software perspective. Okay. So now an attacker, what he can do to exploit this bug is that they can write a program such that the program can cause two illegal requests to the AXI memory interconnect, and the second one can go through. And this way, they can access protected memory ranges that they are not supposed to access. And there are many bugs of this sort. And from the competition perspective, people were able to detect many bugs, but some bugs were difficult to detect. And some teams detected some of those bugs, but and then there are classes of bugs that none of the teams were able to detect. And the most interesting aspect is that the teams detected bugs that were not even injected by us. So these are the bugs that we call as native bugs. These native bugs existed in the original design, and the teams detected them, and we were able to report these native bugs to the developers so that they can fix them. Okay, so an example of a native bug is an incorrect logic implemented in the clock, and we all know many of the digital rights management techniques out there use this clock, and a faulty logic here will help an attacker to cause DRM violations. Okay, so study one. The competition, we had like 54 teams. We gave them the Pulpino SOC. For phase 2, we gave them a different SOC, but this time for phase 2, the participants will have only an 8-hour time frame, and they have to detect as many bugs as possible. And these SOCs are not toy examples. They are complex SOCs designed by though they are designed by university teams, they reflect the real world industry setting. Okay, so many teams, they use different types of techniques. So most of them used manual inspection. And the way they did manual inspection, they prioritized high risk areas. They did not treat all the modules equally. They first prioritized security sensitive modules, and they tried to focus on that. They were able to detect many bugs, but many of the cross-layer bugs that they span across different modules, manual inspection techniques did not help detect them. And again, this, as the name indicates, this heavily relies upon the human expertise. And the other one is dynamic verification. And the idea here is people were trying to run simulations and try to detect using, so they will apply random test vectors, see how the module or a bunch of modules behave, analyze the waveforms, and they try to find the bugs. So this was able to detect some of the cross-modular bugs, but not all. And finally, some of the teams, they try to employ their formal verification tools, but they were not able to even check a complete a single module completely. Again, this is because of the scalability of these tools. And again, the other thing is that you need to manually encode the security properties for formal verification tools. And that is a big challenge because there are not many experts out there who can formally encode hardware security properties into these tools. Okay, so on our end, we also ask the question, hey, okay, this competition helped us to identify the type of bugs that are easy to detect, difficult to detect, unable to detect, and so on. But if we know of these bugs, how well the existing industry standard tools can detect this bug? So for that, we conducted a different study where we assume that we know of these bugs, but we want to know how well existing tools can detect these bugs. So, so for that, we used formal verification tools. So we picked two tools widely used by the industry. One is the Cadence's formal property verification. The other one is security path verification. And the idea here is for FPV, you have to write assertions, you have to write security properties, and this tool checks whether the security properties hold true or not. And the second one is mostly through, the SPV is mostly through information flow tracking, and it will tell whether there is an unauthorized access data propagation from a source to a destination. But again, when we tried using these tools, these tools were not able to scale, or mainly because of the state explosion problem. Hardware tend to have many states, and these tools were not able to go and check for all the possible states. And also, there were difficulty that we face in writing the security properties for many of these bugs. So here, I'm summarizing the results. Oops. The main takeaway for you is that many of the bugs people that were able to detect is mainly based on secret leakage or denial of service. So for that, people use manual inspection and simulation techniques. The formal property techniques were able to detect the privilege escalation bugs easily. And this is because you can encode many of the privilege escalation properties easily in these tools. And that's why they were able to detect. But again, it seems to be that manual analysis seemed to be the most popular approach. And as I told you before, many of these formal techniques were not able to scale well. Okay. So again, examples of hot fails. As I told you before, timing is difficult to encode. Hardware plus firmware co-verification is difficult to do. If you have a bug that span across different modules, then it is difficult to detect. And then security properties of these bugs cannot be easily expressed. Okay, so what are we doing now? So currently, we are coming up with new approaches to detect these bugs. Oops. Sorry, I think, and also to that end, we actually need bugs, and there are not many places where we can find hardware security bugs, where we cannot find models of hardware where we can actually test these things, because unlike software community, hardware designs are not out there in the open, especially the commercial ones. But then there have been a lot of open source effort in the last few years, and what we have been doing is to work on take this nicely developed open source hardware, but also injecting bugs that actually reflect the actual scenarios. And in the current work, even though we are developing our own hybrid approaches in detecting these bugs, we are also expanding the competitions from Hackett to other security venues. So for example, right now there is Hackett event. So now it has become a franchise. So now there is a Hackett competition at DAC, at Usenix Security, as well as at CHESS starting this year. And if you're interested in this event, please check this webpage. We are looking for bugs, we are looking for participants, we are looking for sponsors. So let me know if you have any questions I can answer in the breakout room.